Hello, and welcome to this video. In this video, we're going to be looking at the topic of springs. So springs is the second part of materials that we're going to look at. And springs have loads of uses in everyday life. And in physics especially, we can use them all the time in terms of experiment to try and control certain variables and things. So let's look first at this underlying theory of how springs behave. Okay, so we need to define a relationship which is called Hooke's law. Okay, now you'll probably find when you're doing A-level physics, whenever you meet something that is entitled someone's law, it seems very intuitive. Like, it seems completely obvious, and it's like, why did they even have to write that down? It makes complete sense. Which is also the case for Hooke's law. So Hooke's law states that the force that you apply to a spring is directly proportional to the extension of the spring and this part is the obvious part, this part is the not so obvious part, up to the limit of proportionality. Okay, so this is Hooke's law, and this is probably the key part that we need to know about springs. So force is directly proportional to the extension of the spring up to the limit of proportionality. Now, we'll talk about this limit of proportionality in the next video when we look at Young's modulus. But for now, we can just put an equation for Hooke's law here. So we're saying that the force is directly proportional to the extension, which we're going to call the change in length. And actually, if we have proportionalities, we need a constant of proportionality to take us between the two, and that is equal to k. So F is K delta L. This is Hooke's law, and this is in your formula sheet, where F is the force that acts on it. So force, which is obviously measured in newtons. Delta L is the extension, so the change in length that you have, that is measured in meters. And K is what we call the spring constant, which is measured in newtons per meter. Okay. Now, what is the spring constant? What does that physically mean in terms of a spring? This is essentially the stiffness of a spring, right? So if you have a very high spring constant, it means you need loads of force to produce a tiny amount of extension. So you probably experienced at some point seeing a spring that you can't actually pull apart very easily. That just means that spring had a high spring constant. Whereas spring inside a pen that you use, you can squeeze that really easily with your fingertips, so it has quite a low spring constant. Okay. So the physical intuition of this is quite straightforward. The more force you pull a spring with, the longer the spring is going to get, the more it's going to extend. That makes complete sense. Okay. But this allows us to do a lot of things with this, because we can now, and we'll find out again looking at simple harmonic motion, where springs will come back into it. But what we can now look at is, how do we actually work out the value for this spring constant? Because surely every spring has a different spring constant. How do we calculate a value for spring constant? So I'm going to go through it very quickly, just to give you a rough idea of how we do it, and then I'll go through it more thoroughly when we go through the practicals. Okay, so what we would naturally have to do is, so let me move up here and let's look at measuring the spring constant. Okay, so if we're measuring the spring constant, that means that we need to have some sort of clamp stand with some sort of counterweight to stop it falling off. So this here is a counterweight in order to reduce the moments so that we get equal moments on both sides. This is a spring here attached to some mass, which is known mass. Okay, And we also need to attach a ruler here somehow in order to measure the original length before we attach the mass and then the extension of it after we attach the mass. So we repeat measurements of delta L, so how far is it extended for different known masses. Okay, so obviously the more mass that we put on, the more weight we have, since weight would be equal to the mass times the gravitational acceleration. Then we would form a graph of F against delta L, and what we'll find is that you should get a straight line. Okay, and if you were to actually carry this out and see the more force that you apply, you'll actually start to get a curved line at the top here. Okay, and this is why we have to include that idea of a limit of proportionality. So it's only obeying Hooke's law up to this point here. Okay, this is known as the limit of proportionality, because this is when instead of it being directly proportional to L, where the gradient of this is equal to K, it's now changing and its behavior is doing something different. And again, we'll talk about what happens here and why it happens in the Young modulus video. But for now, all that we need to know is that if we have an F against delta L graph, we can calculate the spring constant from the gradient of the straight line that we have. We'll find that it could do something like that if we were to keep extending it, but we're not going to worry about that for now. Usually when we look at graphs though, we can find out first whatever the gradient actually means, but also then what the area underneath it means. So the area physically is just a force times a distance, and we know a force times some sort of distance is equal to an amount of energy. That's the amount of work done. Therefore, the energy under this graph here must also be an amount of energy. And if we're talking about an elastic spring going back and forth, we actually have elastic potential energy. So therefore, we can say that the area is actually the elastic stored energy in the spring. So when it's fully extended, it obviously wants to go back to being not extended, so it will store some amount of elastic potential energy. And that elastic potential energy I'm going to call EP. And that is then just the area of this, which is the force times the change in length divided by 2, because it's a triangle. Okay, and now you can measure how much energy is actually stored inside a spring that you've extended. Okay, now sometimes they won't give you it like, well, this is how it's given in your formula sheet, but sometimes this isn't the most useful form. But we know that F here is equal to K times delta L. So if I were to substitute this F into here, I could also write it as EP is a half K times delta L squared. Okay, so this is also a formula, but let me actually get rid of that because this one is not given in your formula sheet, but this one is. Okay, but a simple substitution into it leads to this formula anyway. And finally, so we've so far got an expression for Hooke's law. We've then seen how can we actually calculate this value for K, so we know what it is for this individual spring, and then how do we actually know the energy stored in that spring, since we have to be doing work in order to extend the spring. How much energy does it take to actually extend it, which is equal to this. The last thing we need to look at is what happens if we put these parallels, these springs attached to one another. What if we use 2 springs instead of 1? How does that affect how much we're extending something? So now let's look at the argument of having parallel and series springs. So you'll notice the language is very similar to that of electricity, because we're going to be doing something very similar. Let's say I want to hold a mass where I have a big mass of a mass M, and I want to hold this with the smallest possible extension that I can possibly get. And what I have, so my equipment that I have lying around in order to hold it straight are 2 springs. So I have 2 times the spring, and I also have a metal board, right? This is just or actually let's call it a light rod. Okay, so it doesn't actually weigh anything. And the question we want to ask is, what is the setup of this equipment that I can actually utilize in order to make this mass cause the smallest possible extension on a spring? And I've probably given it away, so I'm going to choose between either I can put these 2 springs in parallel to each other. So let me look at the parallel setup over here. So if I put them in parallel, how I'm going to do that is I'm going to say, let's have a spring on this side. These are identical springs, so they both have a spring constant K. So K, and that's going to hold a light rod. And then on the other side, I'm going to have an identical spring that's also holding that. And I'm going to attach a mass M on the rod. So instead of hanging it down, I'll just put it there. Okay. Or I can put them in series, and I can say this extension, so this is spring 1 with the spring constant K, and this is spring 2 also with the spring constant K, and I have the big mass M at the bottom of there. So which one causes a smaller delta L? Okay, now you'll probably have some intuition about this straight away, and if your intuition tells you that the parallel one is going to give you a smaller overall extension, I would agree with you. Okay, now let me explain why. I'm going to do it as simplest case is just to balance the forces, right? So if I look at the total downward forces coming down, it's just M times G, right? If I look at the total upward forces, I'm going to call this spring, let me call this one B, and this spring is going to be A. And I have the Hooke's force, basically. So it's the force inside the spring, which is F, which is really just tension. So I have a force here, which I'm going to call FB, and I have a force here, which I'm going to call FA. Okay, so I have this force spread out over these 2 forces, and by conservation, because it's in equilibrium, FA plus FB must be equal to mg. Then on the other side of that, I actually have the force coming down is still mg. However, that same line of force is acting on both of these springs, and because they're in series with each other, they're both going to feel that same force. And so what's actually going to happen is they're both going to extend by the same amount. But because I've got an extension of the top one that's going to be some sort of delta L, and I also have an extension on the bottom one, which is delta L, I'm actually going to get a total of 2 delta L extension, right? If I add on a large mass onto 2 springs, they're both going to extend by the same amount, but because they're in series altogether, I have an extension of 2 delta L. Whereas on this side, they'll both extend by the same amount. However, they've actually got half of the force that's on each of them because it's evenly split, because these springs are identical. And if I've got an evenly split force between these 2, then each of their delta L's are going to be smaller, and they're also the same level. So I'm only actually going to get an extension of delta L, which is actually smaller than the original extension that I have over here. So if you want a smaller delta L, you always want to put them in parallel. Okay, if you want a larger extension, you put them in series. Now, I'm not trying to demonstrate anything that you need to know off the top of your head, like knowledge-based, but I am demonstrating a way to think about these questions. You will almost definitely be asked about parallel and series springs, and you always need to make sure you're looking at the forces that you have between them, and know that if you have them in parallel, the force will get split over the parallel springs, whereas if you have them in series, both of those springs are still going to feel the same amount of force, which is the total force coming down. Okay, so to recap, just here, all we need to say is F is equal to K times delta L, which is Hooke's law. You also need to know the definition of this, which is that force is directly proportional to extension up to the limit of proportionality. Then we can also say that the elastic potential energy that we know is a half F delta L. And now we know that putting them in parallel will always give us a smaller extension than putting them in series. And that is everything you need to know about springs. Thank you for watching.